As I started yesterday with the case of Sol 3, I exposed the basic geometry of the whole space Sol 3 together with some equation for the Gauss map for constant mean curvature surfaces. And I asserted this result, which is obtained with Benoit, and which says that essentially it solves the Hopf and Alexandrov problem in Sol 3. But in Sol 3, as I explained previously, you have a very big problem on the very beginning, and is that you don't know how to construct a constant mean curvature sphere. Okay, so you know that there are spheres, but you don't know what they look like, and you don't know which mean curvature do these CMC spheres have. Okay, so you first need to understand if there are constant mean curvature spheres for a given value of the mean curvature. So we prove that this is true whenever the mean curvature is greater than 1 over the square root of 3. And we also prove that you have the Hopf type uniqueness. There are no other immersed CMC spheres than the CMC sphere we proved that exists, and Alexandrov type uniqueness. That is, there are no other compact embedded CMC surfaces other than the spheres here that we proved to exist. And moreover, if we assume the part of existence, then we also have the part of uniqueness in both senses. Okay? So this is what I'm going to explain. I'm going to prove this theorem using the description of Sol 3 and the description of the Gauss map of constant mean curvature surfaces that I did yesterday. So, what is the plan of this proof? How it's going to be? First, let me recall that the Gauss map of a CMC surface satisfies an equation of this type. We were talking about this yesterday. So A and B are certain explicit rational functions depending on G, and this is a kind of generalized harmonic map equation in the sense that if this wasn't here, that would be a harmonic map equation. So it is, in some sense, a generalized harmonic map equation. So we are going to try to understand the geometry of constant mean curvature surfaces in Sol in terms of their Gauss map, and especially using this elliptic PD that we have here. So then we are going to do the following thing. Assume that you have a constant mean curvature sphere SH whose Gauss map G is a global diffeomorphism. This means you take its Gauss map from a surface, takes values in the Riemann sphere, but in this case the surface, you can identify it. I mean, you are assuming that it is a sphere, so you can identify it by taking a conformal parameter also with the Riemann sphere. So you have a map from the sphere to the sphere, and the hypothesis is that this Gauss map is a global diffeomorphism. By now, this is a hypothesis. Okay, so associated to this sphere, we are going to construct a certain quadratic differential. You can think, for instance, of the Hopf differential or on the average Rosenbear differential in homogeneous spaces. So we are going to construct a quadratic differential having these properties. First, it vanishes on the sphere. We are going to construct the quadratic differential so that it vanishes on the sphere we are given, and if it vanishes, it means that we are on a piece of the sphere. So the condition of being 0 characterizes the spheres. And on the other hand, we are going to prove that it must vanish identically on any other constant mean curvature H sphere. So if we put these two things together, we are proving that any constant mean curvature H sphere immersed in Sol 3 is actually the sphere we started with, just simply by putting these two assertions together. As I said previously, this differential will not be holomorphic and will not be explicit. It depends on on the sphere we start with. If we had explicit constant mean curvature sphere in Sol 3, this thing would be explicit, but we don't have them, so we just define it in terms of this sphere. So the problem is now whether, that would solve the problem if we knew that there are spheres whose Gauss map is a global diffeomorphism. It seems to be like a strange hypothesis on the theory. But now one key step will be to prove that if you have a constant mean curvature sphere whose index is 1, as I explained previously the notion of index yesterday, that is, it only has one negative eigenvalue for the Jacobi operator, well, for minus the Jacobi operator, then this hypothesis implies that the Gauss map is a global diffeomorphism, and moreover, the condition that the Gauss map is a global diffeomorphism implies that the spheres are embedded. So this puts you in the ground of stability things. And once you are in that ground, you can apply a lot of techniques. And in that case, we're going to prove that you can deform index 1 constant mean curvature spheres into other index 1 constant mean curvature spheres. And in the end, we prove that these index 1 spheres exist for every value of the mean curvature. So we know existence under this hypothesis, which is weaker than the hypothesis of index 1, and we prove that its index 1 spheres exist for all these values. So this is more or less the plan of the proof. Okay, so I'm going to divide it like in two different parts, one regarding existence and the other regarding uniqueness. So I'm going to start actually with the case of uniqueness. Okay. So, as I said, if you want to prove Hopf-type uniqueness, what you usually do is try to find something holomorphic. This is the first thing that we tried. Okay. So what we did, in R3 you have the Hopf differential, which is very simple. And in other homogeneous spaces you have this average Rosenbear differential, which is given by taking the Hopf differential and adding something more complicated to it. So as we didn't know how this quadratic differential could look like in Sol 3, we started looking for a quadratic differential, trying to get something holomorphic, or of a very, very, very general type. This is so we wrote that equation. You have that the CMC surfaces are determined by the Gauss map. This is what says the representation formula. So you can read all the basic geometry of the surface in terms of the Gauss map. So it's natural to try to write something just in terms of the Gauss map. So you need to write something like Q d z square, such that Q depends on the Gauss map, or maybe on some complex parameter, but such that it is invariant when you do changes of conformal parameter. That is, so that this is well defined and that's not dependent on the complex coordinate we are working with. So for doing this, you cannot put here the derivatives that you want. You have to put some very specific things. This is invariant, this is invariant, and you can place some other parts which are also invariant, but which don't give any information, so I'm going to skip them. So this is basically an extremely general differential, because L and M can be any function. Okay, any function. L and M are functions. In principle, from the Riemann sphere into, well, let us put it into C. Maybe even into C bar. Okay, so you have like two functions like this, very general, and you want to know if there are some of them such that this differential gets holomorphic. So you compute. Okay, and for the computation it is very good because you have the equation for the Gauss map in terms of these functions a and b. So you do qz and you arrange things depending on the derivatives of gz and gz bar. So you have like four different terms. And the functions a and b that were in the equation of the Gauss map equation appear. So we need this to be 0. Essentially, for a very general, if we want it to be for any g, what means is that we need L and M to satisfy that this is 0, this is 0, this is 0, and this is 0. Okay. So we first look at the last two ones. You have here an equation M. I'm writing, maybe for the notation, in order to be clear, I'm writing M as a function of Q and Q bar, when Q is just the complex parameter of the Riemann sphere. Okay, so this is what it means. Okay, and the same for L. So I have a function of two different, of Q and Q bar, and I want to understand if there is a solution to this equation and to this other equation.
Is the Q on which side of the
the parameter domain. It's the parameter. So it's, yeah, here you put Q.
I thought you were using C, but Q is a varying point.
Okay, you have the following thing. I am using here two different parameters. One is Z, which is the conformal parameter of the surface. Okay, so you have a surface into Sol 3 of constant mean curvature H. And you have here a complex parameters set on the surface. And so you take the Gauss map, which also has this complex parameter. And now I'm looking for some functions, L and M, defined from C bar into C bar, different from that, which to some Q, you have some function, well, L of Q and some function M of Q. And what I'm going to do is to compose the two of them. I'm going to put, let's say, L composed with G. That would be a map from here into here. So that is the notation. Okay. Okay, so it turns out that this, if I want this and this to vanish simultaneously, it turns out that the system is integrable and has an explicit solution. If we choose this function, very simple, 1 over capital R, where capital R will be this thing, then it turns out that this term vanishes and this term vanishes. So we are in the good way. Okay? But now if I place this M here like this, I have a new system of equations here. Okay? And I have to check integrability by using Frobenius theorem. And it turns out that the equation that you obtain for L is not integrable. So what does this mean? This means that no quadratic differential like this, which is extremely general, can be holomorphic. So essentially this is telling you that in Sol 3 you don't have quadratic differentials, reasonable quadratic differentials that are holomorphic and that are left invariant. So you need to look for another way. It is telling you that something like average Rosenbear differential here does not exist. So what is the way that we look? If we go back to the proof of Hopf, the proof of Hopf was telling the following thing. You start with a constant mean curvature sphere. You want to prove that it is totally umbilical. Then you know that the Hopf differential is holomorphic. But the Hopf differential being holomorphic implies that it must vanish on any topological sphere. And this is the only place where we use holomorphicity, to say that if it is defined on a whole sphere, it vanishes identically. But this condition can be also attained by other weaker assumptions than holomorphicity. So one of them is the following result that is due to, well, to Jürgen Jost and also to Alencardo Carmo Tribuce. And it says that if you have an inequality like this, okay, you have some holomorphic function Q, and you differentiate with respect to Z bar, and this is less than or equal to a certain function f multiplied by Q, where f is continuous, bounded, and positive. Then the function Q is something here, which is continuous, multiplied by something like Z minus Z0. Okay. Okay, this is something bounded and not problematic, and it doesn't vanish, and you have that the 0 is like this. So it is telling you that zeros have a negative index here. So now we can use the Poincare Hopf theorem. The Poincare Hopf theorem says that that on for instance on a sphere the index should be positive. Okay, it should be 2 actually, but for any vector field. But it turns out that if you have that equation, this equation here for some continuous function, then you can define this vector field, imaginary part of Q, dz square, and this vector field. Well, what is telling you this is that this vector field has negative index. So by the Poincare Hopf theorem, it is impossible on a sphere, okay? Because the sum of all the indices of all singularities should be positive. So the only possibility in order to have this is that Q equals 0. So to sum up all of this, rather than asking just Q or Z bar equals 0, which is what we were looking for in order to be holomorphic, we can ask for a weaker condition, which is this one. So how can we look now for this weaker condition? There was something good in the computation we did previously, and it was that if we fix M of W equal to this thing, then, well, okay, here I was using Q as the parameter domain. For some reason, now I have W, but it's the same, okay? So just Q is, I just changed notation, but it's the same. Okay, so if you chose M like this, then Q set gets simplified by that expression. Okay, so, but now you also have the definition for Q. The definition for Q was L of G, G set square, plus M of G, G set, G bar set. So if I do the conjugate of this, I get L bar, G set bar square, plus M bar, this thing. Okay, this is the conjugate. And if I put this Q set, so let us look at the inner part of this. You have Q set bar here and G set bar. So this is telling you that well, Q bar here I could do like this. I go G set bar. Okay. So this part inside is very much like the part inside here, just because of the types of things that you have, because of the derivatives of G with respect to set bar, and these things are the same. Okay. So what I can do is try now to arrange things a little bit. So more or less, I'm not going to do the whole computation, but I mean, I want to put here Q bar. I want to put here Q bar. So what do I need for that? I have that Q set bar equals, I'm going to multiply and divide by this thing here. And you have something, I'm going to write it like that, 1, G set bar plus another something multiplying here G set bar square. So, but this is very similar to, as I said, to this equation, to the equation for G bar. So the idea is that if this first blank thing, I mean this first well, rectangle thing sub 1 would be like one of those, and the other would be like the other one, we would be able to make this better. So I can put this one. Well, I cannot see actually now the other part of the blackboard, but I think we'll put this like, if we wanted this to be L, okay, I want this to be L. So what I do is to put here G set square, I put outside all this part 1 divided by G set bar square and divided by L, and so I can put here L, G set, it's L or it's M? Sorry, let me wait a minute. No, it's M. It's M. I put here an M. And you have here G set bar plus something 2 divided by something 1. This is an M. And this is G set bar square. So it turns out that this is pretty much the same as Q bar. So if this thing was equal to L, I would have here Q bar, and so I would have more or less I would have something like this thing. So it turns out by doing this that if the function L that we have here solves this system, which is basically this equation that I put here, L equal to this thing that was here divided by this thing that was here, M, then it turns out that we actually have this equation. So the basic thing that is telling all of this is that we were looking for something quadratic differential doing like this, and it turns out that if we find a solution to this equation, then this is satisfied, and so we have that this differential should vanish on constant mean curvature spheres. So the problem is whether we can find a solution to this. Okay. Okay, so now I need to state, I need to state the uniqueness part. So assume that this is assume the following hypothesis. We are given a constant mean curvature sphere whose Gauss map is a global diffeomorphism, G. Okay, so I put SH, and it has the Gauss map is a diffeomorphism from C bar into C bar. And it also, G also satisfies, well, the Gauss map equation because it is a constant mean curvature sphere. So I want to construct a certain Q having three properties, basically. Q on the sphere vanishes identically. The second property is that if Q on the sphere vanishes, if Q on some surface vanishes identically, then the surface is actually a piece of one of those spheres, that is the condition Q equals 0 up to left translations characterizes the sphere SH, and I'm going to prove finally that, well, Q set is equal to some f of Q, so Q equals 0 on topological spheres. Okay, so this thing we know, this is the the Jost and Allen-Cardo-Garbo-Tribuzzi theorem, so it is clear. So I need to prove these three facts. Okay, so I have the hypothesis that the Gauss map is a diffeomorphism. So how can I construct a quadratic differential in terms of the Gauss map that vanishes on the sphere we started with? So I was looking for something like this. Some L, G set bars, plus M, G set, G bar set. Okay. So what I want, if I write it in terms of the Gauss map, capital G, of this sphere, it would be something like this. Okay. And I want it to be 0. Okay. I want some differential like this, which is 0 on the sphere. It turns out that C set is always different from 0 because otherwise we will have a branch point on the surface. Okay, so we can just quit these two terms. So this makes an equation. M, this is something known. I wrote the equation for M previously. So I can write here L, let us call it of G of Z equal minus M of G of Z G bar Z divided by G set. Okay, so in case I want something to vanish on the sphere, I need to put this here. If I put this function here, it vanishes on the sphere. But now this depends on the complex parameter set. But it turns out that as G is a diffeomorphism, okay, so this is just a change of parameter of the sphere. Actually, G of Z is a change of parameter of the sphere. So we can assume that L, sorry, is a function from C to C. Okay. So this is what I do here. Okay, this is the function we started with, and I define L of G by this equation. So L is a solution to this. And so if I take now the quadratic differential, once I do this, I can define a very general quadratic differential on the surface. I define, not on the surface, on any CMC surface. I define the quadratic differential like this. Okay, so this is a very general quadratic differential for where M is defined by this and L is defined by this. And you can define this quadratic differential on any constant mean curvature surface. Any constant mean curvature surface, you can define this thing. And we know already that by construction it vanishes on the sphere. Okay, by construction, because of the construction that I did here, it vanishes on the sphere. So now I have to prove, for instance, that it only vanishes on spheres. That is, the condition Q equals 0 characterizes the property of vanishing on a sphere, or the property of being a sphere. So the idea is the following one. I have that for the index 1 sphere, SH, for which I am assuming existence, we have this equation. By its proper construction. And if we had some other surface whose Gauss map satisfies Q equals 0, then we would need something, we would meet some equation like this. So we have like a system of two different equations, and we wish to know the relations between capital G and the usual G. So it turns out that capital G goes from, well, from C bar into C bar, and the other G goes from a certain surface sigma into C bar. Okay, so, and this is a diffeo. This is a diffeomorphism, capital G. So I can go this way by means of a certain function, let us call it phi. So what you have is that G composed with phi is the small g. Phi is, you don't know what is phi at first, okay? Phi is just small g composed with, with the inverse of capital G. So you don't know what is this. But now you can differentiate this with respect to Z bar. And if you do like this, then some equations, you start using these relations that you have here, and you play a bit with the equations, and you rule out some conditions that cannot hold. In the end, it tells you that GZ bar is equal to 0. So it is telling you that this map, that was the composition of the two things, is a holomorphic thing. In other words, we are not changing the conformal structure of the surface. That is, what we are going to, this Gauss map is simply taking the Gauss map we started with and doing a conformal transformation to it. So it's essentially the same map up to a transformation of the sphere we started with. But we know that the Gauss map determines the sphere. This is the representation formula. The Gauss map determines the surface in general. So as we have the same Gauss map up to a conformal transformation, we actually have the same surface. This is the condition. So this differential we have defined is very good because it vanishes exactly only on pieces of this rotational sphere that I'm assuming to exist. And now the final thing would be to prove that it necessarily vanishes on any other constant mean curvature sphere. So what you need to prove, in order to prove that, well, I'm going to prove the following slide. Okay, oh, this is what I said previously. Sorry, I thought I needed to say here. Okay, so for any constant mean curvature sphere, we define this thing. And we already know that Q vanishes on the sphere and actually vanishes exactly on this sphere. It doesn't vanish on any other place. Now I need to prove that this thing is satisfied. Okay, but how do I prove that this thing is satisfied? Well, it turns out that I have defined L by L of G of Z equal minus M of G of Z GZ divided Z. This is the equation for which I define L. And I said previously that there was some equation for this function L such that if the equation was fulfilled, then this condition was verified. Okay, I said previously, if we have one solution to this equation, then you have this equality, which is what we are looking for. So I only need to prove that this actually verifies the equation, well, I don't know what it was, sorry, this equation. I just need to prove that the function defined by this verifies this equation. But this is just computing, okay, so you just do L of G of Z bar, this Z bar, and you use the Gauss map equation. And some other computations tells you that indeed this function satisfies the condition we were looking for. So, okay. So you have this, and so the last statement, that it should vanish on any topological sphere. Okay. It is, in some sense, quite amazing that, okay, we defined the Hopf differential looking for like these two conditions. It vanishes on any sphere, and it characterizes the thing. Okay, but the computation that we did like this was only a sufficient condition for proving that you could prove that that it vanishes on sphere. So it turns out that this sufficient condition we were looking for is exactly the equation that satisfies this L. So I mean, this is quite well, I don't know. It is quite unexpected. Okay, so with this we have the desired uniqueness in an unfinished beta version, let's say. Okay, so the thing is that we have to put a hypothesis. Assume that for a certain value of the mean curvature, you know that there exists a sphere whose index is 1. Whose Gauss map is a global diffeomorphism. Then it turns out, on the one hand, that you have a Hopf type theorem. This is the unique immersed constant mean curvature sphere. It is not said here. You have it is the unique immersed spheres, and it is the unique embedded constant mean curvature sphere. So it turns out, I'm not going to go into detail this, but it turns out that if you have a sphere whose Gauss map is a diffeomorphism, then it is embedded. Okay, you have a sphere, and G is a global diffeo. Then it is embedded. If you see it in R3, it is clear because surfaces which have global diffeomorphisms are convex, so they are embedded. Okay. In this case, you cannot do that because the Gauss map you always left translating to the origin, so it isn't clear what this means. But in any case, we have further information in that situation, and it's that by uniqueness, okay, we know at this point we know that spheres are unique. What does it mean? It means that if I have some sphere, well, maybe immersed, okay, but I'm putting this embedded. Then I can do a reflection with respect to one of the two foliations, and I can change the orientation of the surface. So what I get is another constant mean curvature sphere with the same mean curvature as the first one. But the theorem says that you cannot have this, except for left translations. So what it means is that the surface, even in the immersed case, you know it has a plane of symmetry like here. And you also have a plane of symmetry like here. So to prove this thing, we use a lot these symmetry planes. And we know how the Gauss map behaves actually along the symmetry planes. So we have a lot of information there, and we can argue that it is embedded.
Don't you need any extra assumption for the second statement?
For this?
The second
This thing? Yeah, sphere. I didn't say sphere. Sphere. It is a misprint. It should say here sphere. Okay, constant mean curvature sphere. Thank you. Misprint. Okay, so this solves the problem, but under an hypothesis, and is that there exists a sphere with this mean curvature. So, does it exist? That's the problem that we need to ask now. Okay, does it exist, this constant mean curvature sphere? Okay, for doing this, I start all the part of existence. Up to now, I have proved that if I know that you have an index 1 sphere existing for all values of the mean curvature, then the whole problem is complete, Hopf and Alexandrov. Okay, so how do I do this? I'm going to relate, as I said previously, this strange fact that the Gauss map is a global diffeomorphism with the question of stability of the surfaces. So let me start giving some definitions. Assume that you are given a constant mean curvature sphere in Sol 3. Then you can construct a normal variation of the surface. Okay, so you take the surface, it's like what you usually do in R3. You take the surface, you take the unit normal at each point, and you go with respect to a certain function, okay, a function, you make a normal variation, okay, it's a normal variation of the surface. Here in R3 you go through lines, here you go through exponential, so through geodesics. So you can consider the mean curvature functional, okay? The mean curvature functional, which assigns to, I mean, if you are close enough to the origin here, you have still immersed spheres. So you can consider this functional that assigns to each deformation that you do of the sphere its mean curvature. And it turns out that if you take the Frechet derivative at the origin of this, what you have is the Jacobi operator. Okay, so this is why the Jacobi operator happens. And so I did the definition yesterday, but let me recall it. If you take now minus the Jacobi operator, then it is an elliptic operator here, and it admits a sequence of eigenvalues, okay? Increasing sequence of eigenvalues going to infinity, where the first eigenvalue is always simple. And the index of the sphere is just the number of negative eigenvalues. Okay, so it turns out that for spheres in Sol 3, you have a very good control on the index, in the following sense. You have, for the Jacobi operator, you have a sequence of eigenvalues, okay? But it turns out that 0, the value 0 is always an eigenvalue for the Jacobi operator, and this is because of this. So I have a surface in Sol 3, I take its unit normal, this is constant mean curvature, I take its unit normal, and I take F, a Killing field. Okay, a Killing field of the ambient space. We know that there are 3 linearly independent Killing fields, which are the ones that generate the 3-dimensional isometric group of the space. So it turns out that if I put this function, the product of the unit normal with the Killing field, then these functions are in the kernel of the Jacobi operator. Okay. So they are called Jacobi functions. By a Jacobi function, I will mean a function in the kernel of the Jacobi operator. So it turns out that the dimension of the kernel is at least 3. At least 3. Why? Because you have 3 linearly independent Killing fields, and the 3 Killing fields are, I mean, the orbits of the Killing fields are non-compact. So a surface cannot be a compact surface like a sphere. It cannot be invariant by any action of these Killing fields. So the dimension of these Killing fields is 3. So the dimension of the kernel is at least 3. You could have maybe other Jacobi functions. You don't know. So this gives you that the index on the sphere cannot be 1. Why cannot be 1? Because you have a sequence of Jacobi of eigenvalues, and one of these values is 0. Okay, one of the eigenvalues, you know it's 0 by this thing. But the first eigenvalue is always simple. The first eigenvalue is always simple, and you know that the multiplicity of the eigenvalue 0 is at least 3. So 0 cannot be the first eigenvalue, so at least you have one negative eigenvalue, which is telling you that the index is, well, greater than or equal to 1. Okay, and moreover, you can understand what happens in the case where index is 1. In the case where the index is 1, you know that there are, well, the 3 Jacobi fields here, and they span, well, and they lie in the kernel, but you can prove that they actually span the whole kernel. You don't have any other Jacobi functions other than the one coming from Killing isometries. Why is this? This by a theorem of Cheng, which says that if you have an operator like, well, minus Laplacian plus V on a sphere, well, I think this is not necessarily a sphere, then the dimension of the subspace associated to the second eigenvalue is always less than or equal to 3. Okay, the second eigenvalue is always of dimension less than or equal to 3. So in the case that index is exactly 1, this means that the 0 is the second eigenvalue. So this implies that its dimension should be at most 3. but we know that it is also greater than or equal to 3, so this implies that it is actually generated by all these Jacobi functions. This is very important in order to make afterwards some deformation of the surface. You know that index 1 implies that you know what is the exact kernel of the Jacobi operator. Okay, and so now we have this sequence of implications. Assume that you have a compact constant mean curvature surface in Sol 3. Okay, then we have that A implies B and B implies C, where we have the following. Any solution, A is that S is a solution to the isoperimetric problem, and it implies directly that the index is 1. This is simple, okay, because we know that if you have a solution to a isoperimetric problem, that it is weakly stable. Okay, I mean, if it is weakly stable, it cannot have two different negative eigenvalues, because if you were able to, if you had two different negative eigenvalues, you could make a linear combination of them such that the index form associated will contradict stability. So you cannot do this. So you can have at most one negative eigenvalue, but you always have at least one. So, I mean, this is clear. This is a general property of the isometry, or the isoperimetric problem. And the key for what we are doing here is that we are able to prove that if the index of the sphere is 1, then the Gauss map should be a global diffeomorphism. So this links the whole theory of stability of constant mean curvature surfaces with this strange hypothesis we put that we needed for Hopf theorem, which was that the Gauss map is a diffeomorphism. So I'm going to prove this not in Sol 3, but I'm going to give the idea in R3. Once you have the idea, it should be clear that it should work in Sol 3. So I'm going to assume by contradiction. Assume that you have an index 1 sphere whose Gauss map is not a diffeomorphism. If it is not a diffeomorphism, maybe you have something like this. Okay, so this is a sphere which is non-convex. Its Gauss map is not a diffeomorphism, and actually it fails to be a diffeomorphism more or less by some curve around here. Okay, so these are points where the unit normal is not a diffeomorphism. So let us take one point here. Let us call it P dot. Okay, and here we take the unit normal. Well, we have a lot of different directions. We take the plane orthogonal to this n of P0, and we take, okay, there are many vectors on this plane which are orthogonal to this thing, okay? But it turns out that by hypothesis, this thing has rank smaller than or equal to 1, okay? I'm assuming that it is not a diffeomorphism, so there is a point where it is not a local diffeomorphism. This has rank less than or equal to 1. So there exists some non-zero vector in R3, constant vector in R3, such that it is orthogonal to all these, well, to all the differential, and it is also orthogonal to n. Okay, you have these two things. Okay, it's simultaneously orthogonal to the two of them. But now what you do is to consider at P dot equals 0. You have those two things. But also, as we have said previously, this is a constant, so in particular this defines a killing field in R3. This is the unit normal. So you have that the Jacobi operator acting on this function u is equal to 0. And as Benoit said previously, you cannot have, I mean, you have functions in the kernel of this, its zeros are very restricted to satisfy some conditions. So in this case, one can prove a theorem that says that if you have, this is also a theorem by Chen, which says that if you are on a sphere, on S2, and you have a solution to, well, a certain operator, let us call it like this, and you have lambda2 to be the second eigenvalue, then you have something like this. You have, this is the nodal curve, and you have two nodal domains. Let's call it plus and minus. So the nodal curves is regular and separates two nodal domains. This is important, that this is index 2, that this is second eigenvalue and that you're working on the sphere. But this contradicts this fact, because what we are doing here, okay, this function is on the nodal curve because it vanishes, and its differential is 0. What it would mean here, if we view it in the picture, it will mean that apart from this nodal curve, you have a nodal curve like this, but there will be another intersecting one. And so on a sphere, you cannot continue them making that there are just two nodal domains. So this cannot happen. This contradicts the property that the lambda 2 is the second eigenvalue. That is, it is contradicting the index 1 property. So this means that you cannot, the Gauss map cannot fail to be a local diffeomorphism, so it's a global diffeomorphism by topology. Okay, so you can prove this thing easily using this thing on the dimension on the nodal domains of the second eigenvalue. Okay, so I'm going to prove now using these parts. I am going to prove now that the existence result, there exists index 1 spheres for all values of the mean curvature. And in particular, if we prove that this exists for every h greater than 1 over square root of 3, by the uniqueness result, they will be unique and we will have finished the whole problem. So how do I do this? The idea is the following one. I'm going to start with a very, very small constant mean curvature surface. That this constant mean curvature sphere, that this exists is by the isoperimetric problem. You always know that, that solutions of the isoperimetric problem are compact embedded, and in Sol 3 by the Alexander reflection are spheres, so you know that there is a small sphere here. And I'm going to start perturbing it by means of other constant mean curvature spheres. So I'm going to start to find larger and larger constant mean curvature H spheres. In order to do this, it is very important that the spheres have index 1. And it is actually true that in the whole process I'm not losing the property of index 1. So this is the main, I mean, the key, I mean, the key idea. So I'm going to explain it more with some detail. Formally, I take the interval of all the positive values of the mean curvature for which the sphere exists. Let me explain that you cannot have minimal spheres in Sol, because you could apply, well, it would contradict the maximum principle because you have planes, so it would contradict the maximum principle there. So constant mean curvature sphere should have mean curvature different from 0, so we can orient it so that the mean curvature is positive. I put this set here. It turns out that this set, as I said previously, is non-empty because you have isoperimetric spheres. I want to prove that it is open and closed. Okay, so for openness, this is simple. This is an application of the implicit function theorem. How do you do this? Well, I mean, I'm not going to explain the details, they are in the notes, but how do you do this? If you have an index 1 sphere, as I have explained previously, you know very well which is the kernel of the Jacobi operator. The kernel of the Jacobi operator is exactly generated by the 3 Jacobi functions generated by the 3 ambient killing fields. So you have a very good control on the kernel. And for applying the implicit function theorem, I mean, if you have a good control on the kernel, it is easier. So you have to deform a bit the functional, but they are just classical methods, and you can apply implicit function theorem to prove that this sphere that you have, any of the index 1 sphere that you have, can be defined analytically by 2 other constant mean curvature sphere near. Okay, so the condition is open. Still, you need to check that the new spheres that you have index 1. Okay, but this is by the following argument. This is just by continuity of the eigenvalues. There is a theorem which says that if you deform analytically, then the eigenspaces and the eigenvalues deform analytically also. So you have an index 1 sphere. So you have 1, 2, 3, 4, 5. Okay. Okay, so okay, you have 0, 0. This is always negative, and the next one always needs to be positive. Why? Because we know that the kernel of an index 1 sphere, I mean, we know that the general result by Cheng says that the dimension of the second eigenvalue content with multiplicity is always less than or equal to 3. Okay, so for the sphere, this is greater for the index 1 sphere. But now you do the deformation. In the deformation, how can this? How can the property of having index 1 be non-satisfied? Well, you also have by geometric reasons that these three eigenvalues are 0, so this lambda 5, in some sense, should jump to be negative. That is the only way in which you can lose the property of having index 0. But as the process is continuous, the only way to jump is that it becomes 0 at some point. And this is impossible because you have always that these three are the same ones, and this would violate this result. You have then that the dimension is 4-dimensional for the second eigenvalue, and this is not possible. So this always has to be locally apart from that. So this proves that in the deformation, by this continuity thing, you have always index 1. So what could go wrong in the very last sense? Okay, I need to prove now that it is closed. For proving that it is closed, what I need to prove is that if you have a sequence of constant mean curvature spheres in index 1, I can extract a subsequence that converges to some other constant mean curvature sphere. Okay, how could this not hold? Okay, the problem that it could not hold is, as I said yesterday, that these spheres could converge to something maybe non-compact. Okay, to something maybe going like this or something like that. Okay, so in order to prevent this, I need an estimate on the diameter. So assume that for one moment that I know how to prove that the diameter of the spheres are uniformly bounded. Then, in that case, I can also prove that the norm of the second fundamental form of the sphere, this is a computation, is uniformly bounded. So you have diameter estimates. You can prove that. So you have local area estimates on the spheres. You have bounded second fundamental form. Okay, so then you know that this should converge to something. But as the diameter of the spheres are uniformly bounded, it converges to something of bounded diameter, and so it converges to something compact. And you can prove that the thing that it converges to is actually a sphere because you have symmetries. So this is the idea. This is a convergence process. So in order to show that this is closed, I only need to prove that this diameter estimate. And this diameter estimate, this is the only part of the whole proof in which this constant will appear, and the only part in which the result is not sharp. Up to now, everything was absolutely sharp in some sense. This is the part where it is not sharp. So how do we do this? We need to use, the key is that we need to use a result of Harold Rosenberg, a very general result that is not specific of solve 3, and actually it does not distinguish solve 3 of other spaces like H2 cross R or things like this. So it is very unlikely that indeed it is optimal. The argument Rosenberg says that if you have a surface S of constant mean curvature in some 3 manifold, homogeneously regular, which is stable and with boundary, and you take a point on S, then the distance of the point to the boundary of the surface is smaller than or equal to, let me see, 4 pi divided by this thing. And here I have to put okay. This is the result by Rosenberg. Oh, sorry, strongly stable. Okay, so how is this? Strongly stable means that the index function is positive definite. For zero boundary conditions. So how is this related to our problem? Assume that you have one of our spheres. Okay, this is the index 1 sphere SH that we know that they exist in some cases, and we want to prove, for which we want to prove this height estimate. So what I do is I take a point here, let us call it P, and I consider B of rho to be the largest geodesic ball in the surface, which is strongly stable. So I have something like, well, like this, okay? This is B rho. So now I'm going to take some positive epsilon, and I'm going to work in the complement. So I take here another region. This is epsilon. I'm going to take thing. And so the remaining region of the sphere, I call it omega. So I'm taking the whole sphere and I'm dividing it into two components, leaving a small strip in the middle. Okay. So I know that this is strongly stable. I claim that omega is strongly stable. Otherwise, if it was not strongly stable, we can find a function whose index form is negative here in all this part with zero boundary conditions. But it turns out that if I consider the largest region here, like the ball with this radius, by hypothesis, as this is the largest geodesic ball, this other one should also be unstable. Okay, so you have two different unstable things. So this means that you can create on the kernel of the whole sphere two negative eigenvalues. But this is impossible by index 1. Okay, you cannot have two orthogonal. You cannot have orthogonal negative eigenvalues on an index 1 sphere. So this tells you that this domain is stable and this domain is stable. But now I can use the Rosenbear estimate. So this is less than or equal to this condition on omega and also on the upper part. If I make epsilon go to 0, I have that the diameter, the total diameter is 2 times this. So this is the diameter I obtained. So in particular, it tells you that if the mean curvature, if this quantity is far from 0, then you have a uniform estimate for the diameter, and so you know that the subset is closed. So you know that spheres exist. The problem is that this diameter fails to be good when you approach this quantity here. So the final result that we have obtained in that way, well, this is the same result previously. Okay, if we have any value for the mean curvature greater than 1 over square root of 3, then you know that there are a sphere, that it is unique in the Hopf sense, unique in the Alexandrov sense. And moreover, the uniqueness holds whenever you know that the existence of this sphere holds. Okay, and in order to prove that the existence of these spheres hold, well, you need to do the whole process that we made. And our conjecture is that you can sharpen the result so that, and to prove that the family exists for all values of the mean curvature greater than 0. The reason is very clear, and is that in all the process, this constant didn't mean anything. The only way in which we used that constant was for this final result, using the result of Rosenbear of a different theory. So if one is able to understand better the geometry of Sol 3 and how to do a proof that constant mean curvature spheres in Sol 3, which are bounded, which are far from 0, always have an uniformly bounded diameter estimate, then in that case the rest of the proof works, and we would have that all the family exists for all values. And where the family would be then real analytic, and we also conjecture that these surfaces are actually the boundaries of the isoperimetric regions. So in some sense, the conjecture is telling you that the situation in Sol 3 is exactly the situation that you have in R3.
In R3, you have spheres which are unique in all possible senses, and they are the unique solutions to the isoperimetric problem. Every sphere is a solution to the isoperimetric problem. So our conjecture is that this should hold here. In particular, all the spheres should be weakly stable. Okay, this is the conjecture that up to now we don't know how to prove. And so, well, as this is the last lecture of all this lecture series, I think just in the name of the three speakers, I want to thank you for the invitation and for attending these lectures. It has been a great pleasure for us to be able to expose all these results, and so thank you a lot for your attention.
Let me just thank you guys too. Thanks very much.